Okay, 7:45. So let's start setting up. As people get back, they got the coffee, water, the beverage of the choice. So Michael, if you want to start setting up the first talk of this session, as everybody's setting up, hopefully then so difficult to without seeing faces and without hearing everybody. But welcome everybody to the second session. I want to thank all of the organizers for this fantastic, and look at the turnout, 175 participants and more. Our first talk of this session is going to be by Michael Strauss, the discovery and study of high-redshift quasars with the survey facilities of the 2020s.
Okay, thank you. I imagine everyone can hear me. I'm delighted to have the opportunity to give this talk, and I'm looking forward to an exciting discussion for these 4 days. So let's go ahead and get started. This is just a brief outline. I'm going to start by putting a focus on the work that I've been involved in on HyperSuPrimeCam, doing surveying for low luminosity quasars at high redshifts. Our acronym is SHELQ, Subaru High Z Exploration of Low Redshift Quasars. I'll then talk a little bit about some of the unusual populations of high redshift quasars and talk about some of the scientific theme that the study of these objects and others at high redshift have led to. And I'll end with a view towards the future, Rubin and Euclid and JWST. I think a lot of the themes that I'll be talking about are things that we're going to hear out throughout this conference. And I think tomorrow's talk by Feiga Wang and the talk by Cristina Garcia, among others, will be, many of these same themes will come across. So we'll see that repeating throughout this conference. So we all are familiar with the game that we play to look for high redshift quasars. High redshift quasars have strong Lyman alpha at rest rate wavelength 1216 angstroms. We observe it for a high redshift quasar at near infrared wavelengths, of course, depending on the redshift. And with the Lyman alpha forest and the Gunn-Peterson trough below Lyman alpha, one sees almost essentially a complete absence of light in filters that sample the Lyman alpha forest and of course the Lyman limit. And so the name of the game is, I imagine most of you are familiar with, is to look for objects that show extreme colors. For example, at the redshift shown here at redshift 6, between the Z and the I bands. And so we find ourselves looking at diagrams like this. This is from HyperSuPrimeCam. On the x-axis is I minus Z. Notice Z here gets used both for redshift and for the name of a filter. So it can be a little bit confusing which we're talking about. But again, x-axis I minus Z, y-axis Z minus Y, the Y filter going out to about 1 micron. And the name of the game is to identify objects by their unusual colors. So what's shown here in the blue is the locus, theoretical locus of how quasars' colors change as a function of their redshift. This track starts at about 5.5, 6, 6.5, and higher redshift. Lyman break galaxies over the same redshift range have a different continuum of shape and therefore a somewhat different track. And of course, the main foreground that we're worried about are cool stars, main sequence stars, L dwarfs and T dwarfs, and of course there are degeneracies there. So with CCDs, which allow us to go out to 1 micron to the Y band, one can find quasars to redshifts of about 7, or just a bit more. And I think one of the things that we'll hear from Feiga's talk will be the challenge of going to higher redshift, and of course that requires near infrared photometry. So it's really been an amazing time. I was lucky enough to be involved with Xiaohui Fan in the discovery of the first quasars at redshifts around 6, way back in 1999 or 2000. And at that time, I remember thinking, what are we going to do when we have tens of objects? And of course, now the number of objects at redshift above 5.6, which is a good threshold to talk about really high redshift quasars. They're now 365 in this tabulation. I think that's slightly out of date. I think we've now broken 400 in the many different surveys whose acronyms you can see here. Here's another related histogram from Jinyi Yang and Xiaohui Fan showing the redshift histogram of these objects. And of course, For many years, the redshift record was about 6.4. And then, in the last years, we've been going up to redshift 7 and now 7.5. Again, Fega's talk is going to focus on those. I want to talk here about HyperSubPrimeCam and the quasar survey that we're doing there. What we see here is the focal plane of that instrument. It covers 1.7 square degree imager with this enormous corrector. This entire thing is 3 meters tall. And what you see down here is the team that built it. And I should point out Satoshi Miyazaki, who's the PI of this amazing instrument that has been carrying out a 339 survey on the Subaru telescope, which is covered now about 1,200 square degrees. This gives you some sense of how deep one can go. This is actually an image, a depiction of about 1 degree by 1/3 of degree, actually going a little bit, somewhat deeper than the main survey. This goes about to 27th magnitude, and we'll have a chance to take a look at this picture. But as I said, we have about 1,200 square degrees, and to date have spectroscopically confirmed 162 high-redshift quasars in that sample. So the leader of that quasar work has been Yoshiki Matsuoka. Many of you may know him. Maybe he's on here from Ehime University. This is a plot from our most recent tabulation of the discoveries of these quasars. X-axis, there's redshift. Y-axis is the absolute magnitude of 1450 angstroms. The gray dots being sort of the rest of the the world's sample of high redshift quasars. The blue objects are the objects that have been discovered here. HSC goes to an imaging depth of about 26th magnitude. That's a 5 sigma number in the I band, and that allows us to identify objects at quite a bit lower luminosities than many of the other surveys. I'll point out that the survey also finds a number of galaxies, and those are the green dots here. I'll have a little bit more to say about that as we go forward. The previous plot a few diagrams ago was the distribution of objects as one predicts them to lie in this color space, I minus Z, and the x-axis again, Z minus Y. On the y-axis, what's shown here is the observed distribution of the spectroscopically confirmed objects. So the blue objects here, the objects indicated in blue, are the quasars that we'll be talking about. The galaxies are mixed in there. You see they're quite similar colors. There's a modest number of lower redshift O2 extreme O2 emitters, typically at redshift of 0.8 to 1, and a number of cool dwarfs which come in. Although you'll see that in fact that they're actually pretty cleanly distinguishable in colors, and we've done remarkably well as the techniques have gotten refined. The success rate of spectroscopy for high redshift objects is really very, very, very high. So as we're going to low enough luminosities that it allows us to ask questions about the luminosity function in a luminosity range where galaxies, normal non-AGN galaxies, appear. So this is a paper that Yoshiki led from 2018, showing the inferred luminosity function of these objects, again, luminosity at 1450 angstroms. The sort of magenta points here are the quasars. The blue points are Lyman break galaxies from Ono et al. From 2018. And one sees that at about 23.5, the number densities of quasars and normal galaxies actually are coincident with one another. So we're probing down to luminosities where, among other things, we really do want to start thinking to what extent is the inferred photometry of these objects being affected by the host galaxy. And that's something to keep in mind. So one of the things that we can do with these low redshift quasars is ask whether their astrophysical properties are interestingly different in any way other than luminosity, in terms of how do they differ from the higher luminosity objects that we have. So this is a composite spectra on the upper panel. We have an average of, in this case, 75, the spectra of 75 quasars at, again, all 6 and thereabouts over the wavelength range that we have. Remember, of course, at these high redshifts with optical spectrographs, without going into the infrared detectors, one is limited on the spectral range that one can cover. Lyman alpha, of course, the very strong Gunn-Peterson trough. Beyond that, one can see in this case emission line from nitrogen 5, oxygen 1, and really it's hard to convince oneself that one sees any other emission lines, and the rest of the emission lines, of course, are at longer wavelengths and require near-infrared spectrograph to follow up. We have found a population, which I'll have a bit more to say about in a moment, of narrow line quasars, and perhaps we should put quasars in quotes. Exactly what if these objects are truly AGN, we'll come back to. But look at the spectra here now averaged over 18 objects. What you see here is an extraordinarily narrow, a very high equivalent with Lyman alpha line, maybe a hint of nitrogen 5 and not much else. And as I mentioned, we're also finding significant numbers of galaxies. For our purposes, they're contamination, but we can, of course, make an average spectrum of those. And here one sees no, at least in the composite spectrum, no Lyman alpha emission and strong interstellar absorption lines, which are familiar in the high redshift game. So I should have mentioned when showing this composite spectrum of the narrow line quasars, the red line on here superposed is a spectrum composite of narrow line AGN that we found some years ago in SDSS data. Those objects actually are not as extreme as the objects we found at high redshift. You notice that the average Lyman alpha is considerably broader. So let's talk about these high redshift narrow line objects. Masafuse Onoe has led it. Here we can see a very exuberant Masafuse at the telescope and enjoying himself. What one sees here is the spectrum of one of these objects. In fact, I think this is the object that we found thus far that is of highest luminosity among the narrow line objects. Highest luminosity in Lyman alpha itself. You can see the Lyman alpha line is astonishingly narrow, and one really doesn't see any hint of anything else. But an obvious question is what happens when one looks at longer wavelengths. And so this is spectroscopy that Masafuse carried out with Keck Mossfire, 2 hours in Y and 3.8 hours in J. And you'll notice that for this object, one sees the carbon-4 doublet in emission. Notice again, the lines are astonishingly narrow. One sees it as a doublet. One is in quasar work, one is so used to seeing that as a single broad line, but here it is unambiguously resolved into 2 lines as a doublet right here. Really quite astonishing. And so, again, is this object truly an AGN? Well, let's look and see how it compares in a variety of different diagnostics that we might use to explore its properties. Here is a scatter diagram. Y-axis is the luminosity in the carbon-4 line. X-axis is luminosity in Lyman alpha of a series of different populations of objects. For example, well, the object in question, the one that we were just looking at, is here, sort of in an interesting region of diagram where the only other objects that are known in this particular space in a similar region are drawn from a sample of high redshift radio galaxies, which one sees here. Those objects that I had described from SDSS, the narrow line objects, show actually stronger carbon-4 at a given Lyman alpha. Again, the carbon-4 is often somewhat fatter, again, considerably fatter than the lines that we just saw. So here's some numbers to keep in mind looking at this object. Again, the Lyman alpha has incredibly high equivalent width, 370 angstroms, which is just an astonishing number. And in the original discovery spectrum, it's unresolved, the spectrum that I had shown you before. The carbon-4 equivalent width is 37 angstroms with that error bar. That equivalent width is really too high given our understanding of what star formation can do. And here we're quoting a paper by Nakajima et al. Who carry out models of excitation of carbon-4 by star formation, suggesting that one really can't get above an equivalent width of 12 angstroms. So if the line is just excited by star formation. So we take that as a pretty convincing argument, although perhaps not absolutely definitive, that this object and by extension, the other objects that look similar is indeed an AGN. Again, the lines are astonishingly narrow. The carbon-4 line is resolved 120 kilometers a second, which is just a crazy narrow line. Thus far, it's undetected in the first survey. I mentioned that there are high redshift radio galaxies. There are objects with at least similar carbon-4 luminosities. Whether there's radio detection to be made here is something that we'd love to find out, and radio follow-up will be a good thing to do. And we have time with Chandra coming up to see if we can see X-ray photons from this, which would definitely clinch the case if we detect it, that it is an AGN. So, an obvious question is, should we be thinking of such an object, if it indeed is an AGN, as an obscured quasar? And if so, how is the Lyman alpha that we're seeing getting through? Is it really just a classic analog to a low redshift Seyfert galaxy with just astonishingly strong Lyman alpha? These are some of the questions we do not know the answer to yet. We'll have to explore that further. So another way to explore quasars is at high redshift, as you all know, is with ALMA, and much of the work that I'm describing here is led by Takuma Izumi from NAOJ. So all the plots that I'm about to show are to be credited to him. And as you may know, it's just been astonishing that we've been able to study the host galaxies of high redshift quasars, both in continuum and in a variety of emission lines with ALMA. And indeed, this work didn't start with ALMA, and with previous radio facilities had allowed this to go on, but ALMA has now become the workhorse for this sort of work. So what we're seeing here, again, on the left is millimeter continuum, on the right is emission in the singly ionized carbon line at 158 microns in this case, one of the HSC high redshift quasars, one of the shell Q objects, in this case at redshift 7.07. I think this is the highest redshift shell Q object we have thus far. And note, not only is it detected, but again, spatially resolved, and in the emission lines, one can also resolve it spectroscopically, and so do kinematics on the lines as well. So again, the carbon-4 is spectrally and spatially resolved, so one can actually look for rotation in this object, and of course one sees it, which is just remarkable. So we can actually use this to explore the internal kinematics of the host galaxy. We're seeing rotation here, which is I find absolutely amazing that we can do this. So in this particular case, one can fit a dynamical model to the rotation curve in a sense, and one gets a host galaxy mass, which in this particular case is the number listed here, 7.6 times 10 to the 9 solar masses. There's an inclination correction, of course, that goes into that. So there's a variety of uncertainties that we can explore, but it is remarkable that we can get numbers like this. We can also get a dust mass from the continuum emission, and then assume, and it's a huge assumption, what a standard dust to gas ratio might be, typically calibrated much lower redshift. Assuming that it's the same, and that's a huge assumption, we can get a gas mass that's of the same order of magnitude, shall we say, of the inferred dynamical mass. But of course, you'd love to ask questions, well, is any of that mass turning into stars? How would we detect that? And of course, that's one of the themes of JWST, is which I will touch upon at the end of my talk. So this is from that same object, one actually gets a real rotation curve That's the red dots shown here, and one can fit the model. And that's again, ALMA has just allowed these astonishing measurements at high redshift. I had never imagined that such a thing would have been possible, and ALMA is allowing us to do that. Another amazing thing that one finds in this object is that the carbon-4 line is not just Gaussian shape. It looks like, if anything, like a superposition of two Gaussians, a narrow component and a broad component, which has a full width of 900 kilometers a second. It looks as if that there's significant outflows from the quasars itself. There's one or two other cases known at high redshift. Much argument in the literature about whether this is just how common this might be. Further, ALMA studies of such high redshift objects should give us some hints about just how common such outflows are, and to the extent to which that is ubiquitous, and trying to understand how that fits in to our story and our understanding of feedback from AGN, and whether that's an important component of the formation of the highest redshift objects, both the galaxies and the quasars. I'll also touch upon, we're all familiar with the relationship between black hole mass and galactic bulge masses seen at low redshift, the M sigma, or again, black hole versus M bulge relation that one finds here at low redshift. And of course, the question is, how did this evolve with redshift? What does this look like at higher redshift? So these studies have been done with luminous quasars, again, largely, although not exclusively, with ALMA data. This is from Ran Wang et al. From 2016. Measurements of black hole masses, single epoch black hole masses at high redshift versus dynamical masses from basically by looking at the carbon-4 or CO line in these high redshift quasars. And there, for this luminous quasar sample, one sees that the black hole masses are large compared to the dynamical masses relative to the equivalent relationship at low redshift, which for the luminous quasars, the suggestion then is that the black hole formed earlier, and that might be the logical step. But it's interesting to now push that to lower luminosity objects. And here is some hint from a paper from Izumi et al. Looking at still a handful of objects that we have ALMA data for to get dynamical masses, and again make the black hole versus dynamical mass measurement. One sees a variety of higher redshift objects and lower redshift objects that suggest that perhaps when one looks at these lower luminosity objects, one is seeing those objects for which the host galaxy and the quasar, the black hole, have grown in tandem to get onto the low redshift relationship. Okay. Another thing that ALMA is revealing is the evidence for interactions in these objects. This is from Ran Wang et al. From about a decade ago, CO emission from one quasar whose name you see across the top, and one sees a companion to this object in CO. It's not alone, even though in continuum one doesn't see such objects. And indeed, people have long been predicting significant amounts of detectable substructure, for example, in CO or continuum emission for high redshift objects. And this is in accord, qualitatively at least, with models in which interactions are driving much of the quasar phenomenon at these high redshifts. This is from a paper by Roberto De Carli from about 4 years ago, in which this was a ALMA study of a variety of mostly more luminous quasars at high redshift. And in this case, 4 of the quasars show companions, 1 or 2 of which show interactions. And some of these companions are really remarkable objects in themselves, astonishing star formation rates of hundreds of solar masses per year, and suggesting that the quasars, if nothing else, are living in interesting environments. And this is from another paper by De Carli studying the dynamics of one of these objects. and finding just astonishing. This particular object is not just, doesn't just have a companion, but is clearly undergoing an interaction, huge velocity gradients, when actually in this case with HST sees starlight from this interaction. So when one is directly seeing the cause and effect is a little unclear here, but it certainly is suggestive that the interaction is driving the quasar phenomenon, at least in this object.
5 minutes left, Michael.
Yes, I'm sorry?
5 minutes left.
Okay, perfect. I'm going to skip this, except again, another shout out to Roberto and Antonio Pensabene, who have been doing astonishing work. It's not just about CO and C++, but there's an astonishing range of different lines that one with enough ALMA time can go explore in these systems. I'm going to skip this given the time and think a little bit about what lies ahead. So you know, we're in the realm of pushing to redshift 7 and beyond, as Vega will describe. But you know, we have these astonishing facilities that are now coming on: ALMA, JWST, and the 20 or 30 meter telescopes on the horizon. I want to spend just my last few minutes talking a little bit about what lies ahead there. So we all know that the Rubin Observatory is under construction. Here it is in a nutshell: 18,000 square degrees in 6 bands, going a magnitude deeper than the HSC survey, about 5 magnitudes deeper than SDSS, which has been my touchstone. You know, back in 2015, my wife and I stood on the site at which the Rubin Observatory telescope would be built, and here's what it looks like now. She and I were standing right about there, and it's now, this is from some months ago, but you actually see a telescope structure inside a dome. And we're expecting first light with the commissioning camera in somewhat less than a year from now, with the 10-year survey to start in mid 2024 is the current best guess. So this is happening. And I come back to this picture we saw before. This is going roughly to LSST 10-year depth. Multiply this by 60,000 and gives you some sense of what Rubin will be able to cover. We're going to find thousands and thousands of high redshift quasar candidates. How are we going to follow them up spectroscopically? This is a challenge for all of us. And how are we going to do all the science that we want to do with them? So I'll just remind you what Rubin Observatory depth looks like. This is a small piece, a tiny piece, a few arc minutes on the side of imaging data from HSC, roughly to Rubin depth, and one sees that one's just the richness of the data and the crowdedness. There's all kinds of interesting challenges and lots of fun that we'll have in using these data. So I'm a little tight on time, but this is just saying that, giving some numbers, predicting just by extrapolating luminosity functions and others, what the numbers of high redshift quasars that Rubin might find. We're talking about in the thousands. Euclid is coming along, and of course has wide field imaging in Y, J, and H, but so it of course can push to higher redshifts. And here's from a paper by Barnett et al. Modeling what the colors of high redshift quasars might look like in the Euclid bands, and again with this game of extrapolating luminosity functions and redshift evolution, they're suggesting that they'll find 25 quasars up to redshift of 8, and above redshift 8, well, 8 quasars. But of course, we're all familiar with the challenges of extrapolating from imperfect knowledge. So, and the follow-up, of course, will be an extraordinarily difficult thing, because these things will be have all their emission at near infrared wavelengths and really will be quite faint. JWST, of course, has just launched, and we're all tremendously excited about that. And high redshift quasars have been a major theme among those who have time coming up. And I'll just basically end my talk with a couple of the themes that were prominent in the JWST programs that we saw. There's strong hope that we'll be able to actually see starlight from the host galaxies of these objects, at wavelengths longward of 4,000 angstroms. This is from figure that Shuheng Ding made for a proposal that Masafusa Onoe led of a quasar and its host galaxy as might be seen with JWST. One wants to get spectroscopy of in the rest frame optical, H beta in particular, to measure line widths and get a single epoch black hole masses. And I didn't talk very much about the black hole masses. I think we'll be coming back to that, but the great challenge is understanding how those incredibly massive black holes might have formed in such a short time after the Big Bang. I talked about the interactions of quasars that they might be going on, and following up these objects at other wavelengths, I think is good. And this object in particular is going to be particularly interesting and exciting. I was talking about companions and interactions. This is the same figure that we saw before. I think JWST is going to give us fundamentally new insights there. And this is my final slide, and I think I'm out of time. There's lots of questions. We're still trying. The big questions that I think will be a huge theme in this meeting will be how the quasars relate to galaxy formation overall. Now that we can start studying the host galaxies of high redshift quasars, we can start addressing this question directly. And with that, I will finish. Thank you.
Excellent talk, Michael. Thank you so much. Sorry, you missed the clap like everybody else because of the noise on the faces. In the middle of the talk, when you were talking about those super interesting narrow line quasars, you mentioned that you're searching for X-rays. And yes. Ryan Hickox said that you think, first of all, thank you so much for sharing these interesting results. But he asked, do you have X-ray constraints for any of the other low luminosity high-redshift AGN in your sample? And how deep, say with Sandra, do you expect to have to go to detect this?
Yeah, the quick answer is no, we don't really have anything useful yet. I mean, we have, a handful of the objects in the low luminosity sample have, serendipitous X-ray coverage, but no detections. And so we don't have a great deal to say there. We're going deep enough where we hope that we can get something, we'll be able to say something useful about this object. Of course, when one's observing with Chandra at wavelengths, with Chandra at high redshift, one's sampling, the harder X-rays, therefore you're less affected than you might be otherwise by obscuration and other such things. So there's a chance that we'll find something interesting, but we will see how it.
Looking forward to it. Darren Groton also asked, what do you think is driving the higher amplitude of the black hole bulge dynamic mass relation at high redshift? And if galaxies, you want to answer that question first? Go for it.
So the question is for the high, well, maybe I should go back, however many slides it is. The question, I believe, is asking, where is it? It's too many slides. Basically, yeah. Why is it that at least for the high luminosity objects, one sees a higher black hole mass relative to the host galaxy?
I think higher. Well, I don't know if Darren wants to explain a little bit more, but the higher amplitude of the black hole relation, black hole bulge dynamic mass relation.
Yeah. Well, so the statement would one possible interpretation is that for the higher luminosity objects, one is biased. One's always biased when whatever one's observing techniques might be, one is biased or by the objects that happen to have formed their black hole a little earlier than their host galaxy. Those more massive black holes will, with higher accretion, will be the more luminous objects that one first selects. As one pushes to lower luminosity, perhaps that bias is lessened somewhat, which is why a possible story is that's why we're closer to the standard or low redshift black hole mass dynamical mass relationship that one sees at low redshift. Whether that's indeed the case is still speculation, but it's clear whatever we're doing, AGN are being selected as a very special subset of the objects. And we're looking not at your typical galaxy at redshift 6, but these objects that happen to have very massive black holes that are accreting at a very high rate.
So it's also the luminosities, because they have second part to that question that said, if galaxies and black holes are co-evolving due to local physics, why are black holes getting more fuel to grow than galaxies at these early times? But you answer.
I think that's right. I think you're looking. I think we have to be very careful not to imagine that the story that we tell about these extremely rare quasars at high redshift can be directly extrapolated to what a typical galaxy is doing at that redshift. And I think perhaps one of the clues will be the interactions or the environments. I think, again, JWST is likely to give us fundamental new insights, and one can only speculate what those insights might be about the environments of these objects and whether those environments are special. One might imagine that the high redshift quasars are preferentially in the higher density environments, and of course people have been looking for evidence for that, and I think it's fair to say that the story is likely to change with JWST. I'm really excited to see whether they might give us a clue into these questions.
We have more questions here. Roberta said, also thank you for a great talk. And you really pique our curiosity with those narrow line quasars. So
yeah, I'm curious too, indeed.
He mentioned if you have considered the possibility that the narrow line high redshift quasars you're finding having a small black hole masses and creating a high Eddington ratios.
That is certainly possible. I mean, one's basically taking the analogy with narrow line, what are sometimes called narrow line Seyfert ones. These objects are astonishing. They would be very extreme indeed. And observing these objects at rest frame optical wavelengths would be absolutely fascinating. One of the things that happened when we did follow up of, I mentioned the relatively narrow line objects that we found, in this case unambiguously AGN, at redshifts 2 to 4 from SDSS data, the paper by Alexandrov et al. When we did rest frame optical follow-up at those redshifts, one can do that quite straightforwardly from the ground, and observed H beta, for example. In many of those objects, H beta was what was sort of standardly fat. These were not, for many of them, not narrow line Seyfert 1 galaxies, but they were at 48, 61 angstroms at H beta showed broad lines. So the ultraviolet light was narrower, but the extinction, our interpretation or an interpretation is that the extinction is such so that the broad component was not getting through ultraviolet wavelengths, but was not so large as to obscure at rest frame optical wavelengths. Whether there's something similar that will happen for these objects, I really do not know. I mean, that's one of the many questions, one of the clues that we might be able to get to figure out what their physical nature is.
Actually segue perfectly to the next question that it was Marianne's Westergaard about if they are as obscure as you were saying, how do you explain that you can see so well the strong Lyman alpha, the equivalent with?
That is exactly the question. I wish I knew the answer to that. Sorry, I should put these while we're talking. We should just put them up. Just the eye candy is too nice here. Yeah, I mean, astonishing, strong Lyman alpha. So the question is, come up with a geometry of obscuration that allows extended Lyman alpha to shine through with such astonishing strength and high equivalent width. So it's not an easy story to tell. So these objects, maybe they're not quasars, but whatever they are, they're certainly interesting. No, we do not have a full understanding or model of what they mean.
They definitely are. And then Amanda Banerjee also said, very interesting talk. Thank you. Do you have an estimate of the continuum reddening of this also narrow line?
Of this object, so as you can see, the continuum is barely detected here, probably better in broadband photometry. Can you convince yourself that you see a continuum here that you want to measure a slope off of? So the answer is nothing. I don't think we have a continuum measurement good enough to be able to say anything really definitive here.
Yeah, I agree. Well, thank you so much, Michael, for that fantastic talk and for picking the
Thank you so
curiosity of
much.
everybody.
Looking forward
We're
to
gonna
the
move
rest
to
of the
the.
meeting.
Thank you. We're gonna move to the next one, which is gonna be Sandra Raimundo. So you can start setting it up. It's 8 minutes plus 12 questions, so you can start posting them there. Black holes fueled by misaligned gas. So Sandra, the floor is yours.
Hey, hi everyone. Thank you, Paula. So I'm going to be talking about black hole fueling, and more specifically about black holes that are fueled by misaligned gas. So I think most of us are interested in knowing how black holes are fueled. It's important to know how black holes grow and also why some black holes are active and why some are quiescent. And we think that to fuel black holes and to have AGN, we need two things. We need a supply of gas, and then we need the dynamical mechanisms to transport that gas to the central black hole. And the big question now is, we don't know what the origin and the transport mechanisms for this gas are. We don't know if there's, well, we think there isn't one single mechanism that works for all galaxies, but we're interested in knowing, can we determine what these mechanisms are, and can they help us understand why some black holes are active and others are not? And for this talk, this is part of a research into black hole fueling mechanisms in general. And we are specifically looking at black holes that are fueled by external gas. And this is connected with the misaligned gas from the title of my talk. So when I say external gas, I mean external gas supply. So any gas that comes from outside the galaxy. So this could be from mergers or from tidal interactions with neighbor galaxies. And what happens is that during these interactions and gas exchange, often misaligned or counter-rotating structures are created. And this means that there's a kinematic difference between the material that was in the galaxy and the material that comes from outside the galaxy. And this can sometimes be seen in a difference in the orientation of the rotation between the different gas components. And we actually see this in real galaxies. This is an example here. This figure shows a result for MCG 63015. So this is a local galaxy, and with local galaxies, we can do these high spatial resolution studies, and we can look at the velocity of the stars and the gas. And here I'm showing the stellar velocity field for this galaxy. So the black cross here in the center indicates the position of the black hole, and the colors indicate the direction of the velocity of the stars in the nucleus of the galaxy. So blue is velocities towards the observer, and red are velocities away from the observer. And the direction of rotation can be seen here with this label in the bottom. So the central region of the galaxy is rotating in the opposite direction as the main body of the galaxy. So this is an example of a counter-rotating core of stars that was formed after this galaxy accreted external gas. And one interesting thing is that numerical simulations show that when these misaligned structures are present, they could contribute to the inflow of gas to the nucleus. They actually promote inflow of gas. And this is what we want if we want to fuel the black hole. And for this galaxy, for example, we see that the AGN fueling reservoir was replenished by this gas, and the external gas can get down to 50 parsecs from the black hole, which is the resolution of our data. And we also saw in a different example, galaxy NGC 5077. So what I'm showing here is the stellar velocity and the ionized gas distribution in this galaxy. So the top panel shows the stellar velocity. And what I want you to pay attention to is the bottom panel, where the gas distribution is shown in colors, and the stellar contours are in green. So you can see that the distribution of ionized gas is completely decoupled from the distribution of the stars. The gas is almost distributed along the minor axis of the galaxy, and it has these plumes going to the north and south. So what we think is happening is that we are seeing an earlier stage of the external gas inflow. So when the gas came from outside the galaxy and it's infalling to the galaxy, what is happening is that the stellar torques from the disk will be driving the gas to the nucleus. And this has been predicted by numerical simulations as well. So we're seeing the stellar torques aligning the gas, and the gas closer to the nucleus aligns first. So it's likely that for both these galaxies that I showed, the black hole is accreting or will be accreting from this misaligned gas in the near future. So is this important for all galaxies? So we think that it's probably more important for galaxies that don't have a lot of gas to start with. So these are early type galaxies where if you have an external accretion event, the gas that falls in can really make an impact on the amount of gas that the galaxy has available. And in terms of how many galaxies show these distributions of misaligned gas, so we think that in early type galaxies, 40% of the galaxies that have gas have misaligned gas. So this is quite a common thing to see in early type galaxies. And what we wanted to do was also to look at a larger sample of galaxies and find out, is the presence of misaligned gas contributing to having more AGN in these galaxies? So what we did was to look at a large sample of galaxies in the local universe where we could do these resolve studies. And what I'm showing here in the figure is the fraction of AGN as a function of the misalignment between stars and gas. So the two distributions are showed for the one that it's in 0 is alignment between stars and gas. And what's indicated by more than 45 degrees misalignment, that's considered misaligned gas. So what we found is that it seems to, there seems to be an increase in the fraction of AGN for misaligned galaxies with misaligned gas. And of course, the caveat is that this is a small number statistics because they're not many AGN in general in the local universe. But this is an indication that actually in these situations, we may have the two things that we need, a supply of gas and the dynamical mechanisms that drive gas to the center.
Last minute, Sandra. Oh, perfect.
Yes. Yeah. So this is my last slide. Thank you, Paula. So just to conclude, the external gas accretion can replenish the gas reservoir in galaxies, and this is important for galaxies that don't have a lot of gas. The results of these two galaxies that I showed, they are detailed studies. They show that this misaligned gas can be important to fuel AGN. And actually, AGN appear to be more frequent in galaxies that have misaligned gas. And this could be because we are actually having the supply and the dynamical mechanisms to fuel the black hole. Okay, thank you.
Thank you for that great talk. There's a question in the question and answer here in the Q&A. Very nice talk by Ryan Higgox. Very nice talk, Sandra. How are you able to distinguish between inflow and outflow in the extended ionized gas?
Yeah, that's a good question. So we don't distinguish it based on the dynamics in general. So the reason why we say the gas will inflow to the nucleus is based on the numerical simulations for these types of interactions. So there have been numerical simulations that have this inflow of gas in a galaxy that has a stellar disk. And what they see is that due to the stellar torques in the galaxy, it will contribute for the gas to lose angular momentum and flow to the nucleus. And actually, we see that the gas gets close to the nucleus. This is for NGC 5077. And MCG 63015, we actually see that the gas is already very close to the black hole. And this is misaligned gas. So what we can say is that the gas, the external gas managed to go from the outskirts of the galaxy down to the nucleus because we see that it's misaligned, but it's already in the nucleus. So it must have gone through, the path throughout the galaxy. Now, the regions very close into the black hole, we're looking in to see if there's some signatures of inflow there. And this is difficult. So what we're going to do is to measure the dynamics of the gas at very high spatial resolution and try to find some structures that could indicate gas inflow, such as nuclear spirals and so on. But I agree that this, when we get close to the black hole, this is very difficult to distinguish. Yeah.
Thank you so much, Sandra. There are a lot of other questions in the Q&A that I'm gonna ask, or we're gonna move to the Slack. And as you have the note there, thank you for putting it there, Sandra. We're actually gonna have the discussion 24/7, so you can keep on talking to anybody. But thank you so much again for your talk. And our next talk is by Paulina Lira. Paulina, do you wanna try start sharing because we couldn't test it before? We can see you there. There you are, excellent. Can you see, you can unmute yourself and share the screen? Perfect. I think I'm seeing it. Yes. I don't hear you though. Are you unmuted?
Okay, I think now you should.
Yeah, now I hear you. Excellent. So our next talk is about short-term variability in intermediate mass black holes by Paulina Lira.
Hi, hello everybody. Thanks for having me. I'm going to talk about short-time variability in intermediate mass black holes, and this is a list of some of my collaborators. So why to care about intermediate mass black holes? Well, among other things, they can give us some answers about supermass black hole seeds, since normally the kind of black holes, massive black holes that we study have grown through accretion and mergers to be the monsters that we know today. However, those objects that are found in small galaxies have had very little growth through cosmic time. They will have also black holes that have growth only a little, and these objects might tell us something about the mass distribution and the mechanisms of the seeds, the formation of seeds of massive black holes. So here's an example of an intermediate mass black hole. This is NGC 4395 that has this tiny nucleus with a black hole mass of about 10 to the 5 solar masses. And if you take a light curve of that nucleus, you can see something like this. These are different nights, and you can see very strong variability from night to night. But not only that, if you zoom in into just one night, you can see intra-night variability in timescales of just a few hours. And then if you take the power spectrum density of these nuclei, this nucleus, something that Berg did 2 years ago using test data, and you fit a broken power law to this PSD, you can characterize something called the damping timescale. And I think 4395 is this very last point here. And what Berg showed last year was that this damping timescale actually correlates with mass. So it's not just the fact that something small can vary a lot, but also that variation can tell us about the mass of the black hole. Furthermore, we recently have found quite convincingly that the power law actually shifts horizontally as a function of black hole mass, and vertically as a function of accretion rate. So focusing on the dependency with black hole mass, you can say the following. If you shift towards higher and higher frequencies, somehow you're going to be only observing the lowest mass black holes, because high mass objects will have negligible variability. So it's a matter of going to frequencies that will select only small objects to just isolate this population. For that, you need fast monitoring. You need depth, and you need area. So we did this in our sibling survey using data published by Foster et al. And they used DECAM to study for about 1 week 2 large pieces of the sky in 2015 and 2016. And we used this data to construct fast monitoring light curves. We cross-matched this with SDSS and found a sample of fast varying nuclei. You can see the two examples here of two light curves. You can see the aperture photometry we use compared with the stamps of the galaxies. And you can see here, this is one night, another night, another night. And you can see the fast variability of these sources compared with stars and with non-varying galaxies. So we found that about 4% of galactic nuclei show this type of variability, and this corresponds to about 3 objects per square degree. And here we have a distribution of the masses and luminosities of those galaxies, and we see that the occupation fraction is pretty flat, but tends to go up towards low mass black holes. And low mass galaxies, and it tends to go high, obviously, towards low luminosity objects. And we already knew by results, for example, from Baldessera et al., that these type of galaxies rarely show broad components to the Balmer lines. And we find the same with our sibling sample, where out of 500 objects, only 5 of them show broad components to the Balmer lines. So how complete are we? So we looked at this variability, and we found that very few of them show broad lines. We can ask, we can try to do the opposite, focus on objects that we know are bona fide intermediate mass black holes and see whether they vary or not. So we took 9 objects from the Grion and Ho sample of 2007, which show clear evidence for a low mass black hole. Here you can see the range of black hole masses and accretion rates of these objects. And first of all, we obtain a light curve from the Zwicky transient factory for these objects. And here are the light curves. Every bunch of points here corresponds to 1 year of monitoring. And you can see that, yes, all of them vary, and quite substantially. But what about this fast variability that we are predicting for these sources? And for that, we did some monitoring ourselves. And here are some of the light curves we obtained. Look that these times, the x-axis is hours and not days as before. We obtained data from 2 different observatories, and each one of these groups correspond to a different night of observing. And you can see that, yes, most of them show clear evidence for intra-night variability. This is another group of sources. So I end up with my conclusions that fast variability is most likely the most efficient and reliable method to isolate and find intermediate mass black hole candidates. The problem is that right now, if we don't have a broad component to the Balmer lines, is how we're going to determine their masses. However, we are finding interesting results that show that the study of the variability itself might have that answer to our question. But it's likely that we're going to need large samples of these objects and very good quality light curves in order to pin down their black hole masses. Thank you.
Thank you, Paulina. Excellent talk. With the large samples that you are thinking about, what are you aiming for? What type of samples are you going to try to be using?
Oh, well, we don't have that in hand right now. And unfortunately, I think Vera Rubin will be at the limit of really going into this intermediate mass black hole population. But that's something that we are going to assess in the near future, because of course it's going to be the source of an amazing amount of variable sources in the near future. So hopefully we will be able to use those light curves. They're not going to have the fast variability that we will really like in terms of nightly measurements, but we need to see. We need to simulate and find out what we can get from Rubin.
Excellent. No, thank you. No, those transient objects studies are super interesting. Michael had a question. Strauss, I love to hear more about what Rubin can do for short-time variability studies. Well, I think we just answered it as we, but maybe you can elaborate a little bit more about what Rubin can do for short time scale variability studies. Yes,
yeah, as I said, if I can go back to this is CTF light curves for these objects, and I don't know whether, let me play this for you again, whether you can read the y-axis. These are all low amplitude variations, but it still looks very, very fast variability, even in terms of years. So I think there is great hope here for Rubin to give many answers about variability in general and how it correlates with mass and with accretion rate. And I think we might just go into this sample, into this mass regime and try to characterize this population. Yeah.
Excellent, thank you. There's another talk, but we're gonna move that one to Slack so we can move on time for the following one. Thank you so much, Paulina, for that. The next talk is by Laura Sommovigo. So Paulina, can you stop sharing? And then Laura, can you share again? Where she is gonna talk about comfortably dusty, reducing the tension between local and high redshift galaxies infrared observations. Perfect, we can see it, great.
Okay. Do you see them in full screen now?
Yes, excellent.
Okay, perfect. Okay, so hi, I'm Laura Sommovigo, and I'm now in the last year of my PhD at Scuola Normale Superiore in Pisa, where I've been mainly working on dust in high redshift galaxies. What do I mean by high redshift galaxies? I mean galaxies really in the epoch of ionization, so at redshift higher than 5. And thanks to ALMA, it has become possible for the first time to observe the far infrared continuum emission even from these sources. This has unveiled the presence of dust even in galaxies at the epoch of ionization, which was really surprising for most of us and opened up several questions which are still unanswered in our field. For instance, what is the dust content of these EOR galaxies? How do these very young systems manage to build significant amount of dust in such a short time? What is the dust temperature in EOR galaxies? And finally, does the dust temperature evolve with redshift? In my talk today, I'm going to focus on the last two questions. And now let me give you some context on the dust temperature evolution with redshift. Where does this claim come from? In the last few years, several groups working on stacked SEDs at low redshift, where I mean redshift below 5, have found a tight correlation between the dust temperature and redshift. The results that I'm showing here are from Schreiber and collaborators, which fitting the stacked SEDs between redshift 6 and 5 found this very steep linear increase of the dust temperature with redshift, which was somewhat confirmed by latest alpine results between redshift 4 and 6. So what people have been doing after this is to try to understand if this trend was still valid even at higher redshift by adding the few individual sources for which we have available dust temperature estimates at redshift higher than 5. I'm showing here the images of the few sources that we have at redshift higher than 7. And you can see that the situation is becoming more complicated. And in fact, what is puzzling and interesting, in my opinion, is that different groups have arrived to somewhat different conclusions. For instance, Richard Bowens, by doing the fit of exactly the data points that I'm showing here, so stacked SEDs at redshift below 5 and these individual sources at redshift above 5, found a linear relation pretty much consistent with the initial suggestion by Schreiber and collaborators. On the other hand, Liang and collaborators, doing the fit of stacked SEDs from simulations from the fire suit, found a different trend with a significant flattening in the evolution of the dust temperature at redshift higher than 4. So what has really been hindering the progress in this matter is the very few data that we have at the very high redshift end, and on top of that, the very large errors and the wide scatter in the few dust temperature estimates that we have. In fact, you can see that we have sources with temperatures as low as the CMB almost, and instead sources such as Y1 and YD4, which have dust temperatures as high as 80 Kelvin and more. I'm going to come back to these sources in the latest part of the talk. So on top of all of these observational problems, there's an additional issue, which is the fact that neither of the trends that I'm showing relies on a physical model. In fact, they are both fits to either observations or simulations, but we don't have a physical motivation, a clear one for the cosmic dust temperature evolution in the first place. So at least for the lack of data, the recent ALMA large program REBELS can really help us progress further. REBELS stands for Ionization Era Bright Emission Line Survey, and it is a program targeting 40 of the UV brightest galaxies between redshift 6.5 and 9.5, led by Richard Bowens. What we have been doing is to scan for the C2 and O3 line emission and the underlying dust continuum, and I can already tell you that we have several bright detections both in C2 and in continuum. You can find more details in the flagship paper by Richard Bowens himself, but what is really important for the sakes of this talk is that thanks to this survey, we have the first ever statistical sample of redshift 7 for infrared continuum detected galaxies. So we decided to look into these sources. Let me show them to you. These are all the REBELS galaxies that we observe both in continuum and in C2. And look at their infrared SEDs, which are now shown and color-coded according to the dust temperature. So the white points that you see are the continuum observations that we have. And what you might be asking is, how can we constrain the dust properties of these sources, considering we have only one continuum observation? Well, this is possible thanks to a new method that we presented in our paper Sommovigo 2021, where basically we use the C2 and the continuum in combination to derive the dust mass and the dust temperature of galaxies, basically using the C2 luminosity as a proxy for the dust mass, and then the underlying continuum to constrain the dust temperature. But let me summarize the results for the REBELS galaxies. We basically find dust temperatures in the range between 39 and 58 Kelvin, with an average around 47 Kelvin. So going back to the cosmic dust temperature evolution plot, the first thing that we can do, trying to really compare apples with apples, is to add the average dust temperature of the REBELS sample in the stacked SED plot. So this is what I'm showing here. And basically you see that this 47 Kelvin of the REBELS galaxies sits in between the two relations that I was showing before. This means that we cannot discard either, but also that maybe neither of them is really describing the data at the best of our possibilities. But we can do something more. So we can really unpack the stacked SEDs and look at the individual galaxies, both at low and high redshift. And this is what I'm showing here. So these green triangles that you see here are the individual galaxies whose SEDs were stacked in Schreiber's work. And here at high redshift, you see all the sources that we know for which we have both a C2 and underlying continuum detection. In particular, I want you to focus on the REBELS galaxies, which are color-coded according to their continuum observed flags. And on this purple rectangle here, this is the area where we find that the individual alpine galaxies dust temperature lay. And again, we are able to derive the individual galaxies dust temperature thanks to our new method. And the results will be presented in an upcoming paper of mine. So at this point, we could have closed the deal by doing a fit of these observations. But you can see that when we're looking at individual sources, the situation is becoming much more fuzzy and complicated. So we decided instead to step back and address the physical issue, so the lack of motivation for this trend in the first place. I don't have the time to enter in the details, but we came up with a new physical model which connects the dust temperature to the total gas depletion time in galaxies, which is the ratio between the total gas mass and the star formation rate. And in particular, we find that the dust temperature anti-correlates with a power of 1/6 with this total gas depletion time. And this is exactly where the dust temperature cosmic evolution comes into play. In fact, we know that the depletion time decreases at earlier epochs. So in other words, we find that the dust temperature raises with redshift due to the decreasing depletion time at earlier epochs. And this increase is actually milder than linear with a power 1 + e to the 0.42. But you can also notice that there is an additional term in our relation, which depends on individual galaxy properties, and namely the optical depth to UV, tau UV, and the metallicity of galaxies. And this term is responsible for the scatter in the dust temperature observed at any redshift. So by assuming a range of values for these two parameters, we can cut out an area in this plot, and moving from bottom to top, we are moving from lower optical depths to higher optical depths, and from larger metallicities to lower metallicities.
Last minute,
So,
Laura.
Yeah, thanks. So basically, we can explain the very hot dust temperature observed in these galaxies, Y1 and YD4, which I was mentioning at the beginning, with both a large UV optical depth and a very low metallicity. I leave you here to my conclusions, and I'm happy to take any questions. This is also my email, so if you have any additional curiosities offline, please feel free to contact me.
Excellent, thank you. And I'm sorry for Americanize your name, Laura.
Yeah.
I had a question on the, well, I don't see any questions in the Q&A. I'm gonna give a minute for people to like maybe post something. Can you go back one more in the formula, in the physical explanation that you're trying for this evolution of the temperature? Will it follow that it's like that sharp rise at the end towards the galaxies at redshift 8, or would it still miss that if you were like trying to like put that model there? Like my question is whether the super steep rise towards the galaxies at redshift 8 will be matched with your physical model.
I mean, the cosmic evolution, which is this milder 0.42, is shown by this gray dashed line. Then to move at very hot temperatures, you necessarily have to play with these individual galaxy properties. So we can reach these sources with metallicities, as you see, below 110 solar and very high optical depth, but we necessarily have to play with the individual galaxy properties, which in other words tells us that yes, there's a cosmic dust temperature evolution, but that's not the whole story. You know, we cannot really rely only on that to understand some very hot and at the same time very cold temperatures that we are seeing. For that, we necessarily have to rely on the individual galaxy properties.
Thank you. We're going to answer one of the questions of the Q&A. Can you speak a bit about this method of using the carbon tube and a single continuum measurement to estimate the dust temperature?
Yeah, thanks for the question. I have a backup slide on this. So basically, this is the formula that we all use to fit the continuum flux per unit frequency. And once that you have your the redshift of your source and you have fixed the dust model, you are left with two unknowns, the dust temperature and the dust mass. As I was also saying in the presentation, our very simple idea was to rewrite the dust mass as the product of a dust to gas ratio, which we consider to scale linearly with the metallicity, and a C2 to total gas conversion factor, this alpha C2, which is then multiplied by the C2 luminosity. Then we use the Luz relation and the Kennicutt-Smith relation to derive an analytical formula for this alpha C2 conversion factor. And in this way, basically, with one observation, we can constrain both the dust temperature and the dust mass. So let me say this again very in brief. Basically, we use the C2 luminosity as a proxy for the dust mass, and then the underlying continuum to constrain the dust temperature. And in this way, with one observation, we constrain two parameters. And this method has been tested on several local and high redshift galaxies and also on simulations. And in all cases, we recover the same dust temperature that is obtained with traditional LCD fitting, but relying on multiple infrared data within 1 sigma. And this is shown here in this plot, where you have on the y-axis the dust temperature obtained with our method, and on the x-axis that obtained with traditional LCD fitting. And this area is the area around the bisector plus minus 30% uncertainty. And you can see that all these galaxies lay within this area. So that's very encouraging.
Excellent. Thank you for that detailed explanation. Perfect. Well, thank you so much for this talk. And we're going to get to the last talk of this session by Stefano Carniani, Quasar feedback at cosmic noon trace by VLT and ALMA. Go for it.
Okay, perfect. So good afternoon, everyone. So now we are going to talk about quasar-driven outflow. In particular, we're going to talk about quasar feedback. I'm going to show you some results obtained with ALMA and VLT observations. So just a brief introduction. So today we know that power outflow driven by supermassive black hole can have a huge impact on the galaxy properties from small to large scales. Several cosmological models and simulation required such power to outflow to reproduce the properties of the local galaxy population, such as the relation between black hole and galaxy properties and the bimodality distribution of galaxy in the star formation rate stellar mass diagram. So current several models expect that such fast and massive outflows are able to suppress the star formation in galaxies by removing gas, that is the main fuel that used to form stars. Here you can see a plot from a recent simulation by Costa, in which show the effect of the outflow in a quasar redshift between 6 and 6.5. It shows the star formation rate as a function of the radius, and we can see that in only 50 or 100 megayears, the star formation rate in the central part of the galaxy has been completely suppressed or quenched. This is very important. They claim that it's very important. This effect is also called ejective mode, can have a key role on the growth of black holes and also on the evolution of the bulge of the galaxies. So from observational point of view, we want to verify if this feedback is visible in quasar, and to do that, we observe several quasars are redshift between 2 and 2.5, where we expect that powerful are very outflow are very powerful, and they leave a prominent mark on the galaxy properties. We used VLT in particular with Symphony, and we observed the typical optical lines of 3 H beta, H alpha that are redshifted in the near infrared wavelength range. In most of quasar, we detect the outflows, detecting the broad component of the tree, and we're also able to map the outflow. You can see from this velocity map, where we see the direction of the outflow, and we can see that such powerful outflow can reach velocity up to 1,000, 2,000 kilometers per second. Then we use the H alpha lines to trace the star formation activity in the galaxy. And here we can see the map of the H alpha line for different quasars. And we can see that there is a anti-correlation between the spatial location of the star formation activity and the location of the outflows that is indicated with white contours. So we can see that in the outflow region, the H alpha is low or is close to 0. So this suggests the star formation activity is absent or is suppressed by outflows. However, although these observations seems to suggest that there is feedback in action in this quasar, recent works claim that the low angle resolution of such observation are not a clear proof of negative feedback in action, because we are not, it's not easy at this low angle resolution to disentangle the emission of the GN and the emission of the star formation activity in the host galaxy. In addition to that, H alpha, yes, is a good tracer of star formation, but it could be also obscured by dust. So we're able to see only the unobscured star formation activity. So about these 2 points, for the first one, it's obviously we need for the next generation of telescope like GWST. Now we are looking at the evidence of for quasar feedback in other observation with adaptive optics, where we have higher angle resolution. And for several quasar, it seems that there is this the same anti-correlation between the star formation region and the outflow regions. But I don't have now time to go in detail on this part. And for the second point, the idea is to use ALMA to map the dust emission and see if there is an anti-correlation also with the outflows. And now I'm going just to focus in one galaxy. You can see here the outflows on the top panels, and the dust has been observed by Schultz and has been reported in Schultz 2021. And you can see here the dust emission in the red contours. Okay, in this case, the emission is tracing diffuse dust in the interstellar medium, and we don't see any anti-correlation with the outflow region. So in principle, it seems to say, okay, maybe from the dust map, the star formation rate, the star formation activity is everywhere, and we don't have any feedback in action. However, we should be careful when we use dust to trace the star formation activity in galaxy, because the far-infrared emission is a good trace of star formation activity only when the dust is heated by young stars. But when we have a DGN, also the radiation of DGN can hit the dust, and in this case, the far-infrared emission is not anymore a good tracer of the global star formation rate, star formation activity in the galaxy. In particular, in recent simulation, we noticed that in galaxy with an AGN in the center, the dust temperature increases to very high values, higher than 100 Kelvin, and this is due mainly to the radiation of AGN. But another issue, it happens here, because we know that the surface brightness, the luminosity of the dust emission correlates, strongly depends on the dust temperature. And this trend, these changes of dust temperature with the radius can alter our dust map. And you can see an example. Here we have two different dust maps, okay? And the size of the emission is the same, but I just changes the profile of the dust temperature. In one case, the dust temperature is flat, is constant over the galaxy. In the other case, I assume an exponential profile, similar to the one that I showed in the previous slide. And in addition to that, I just removed part of the emission to simulate the effect of the feedback. You can see that in the right case, where we have this exponential profile, it seems that most of the emission is coming from the center. This is just because the temperature of the dust is very high with respect to the dust temperature in the rest of the galaxy. And when we convolve by the ALMA beam, with the typical of the observation that you showed early, we see that in one cases, we still see the effect of feedback or the outflow that is able to remove dust from the galaxy, while in the other case, it seems to we see just a point source. This is just because most of the emission or most of the surface brightness is very high in the central part of the galaxy. So
1 minute.
Yeah, sure. So if you want to see the effect of the outflow on the dust morphology, we need to remove this central component, central very bright component. This is what we have done in one of our quasars, which we see the anti-correlation between H alpha map and outflow region. Here you can see the map from ALMA tracing the dust. In the V plane, we remove the central component that is resolved. And this is the map after removing the central components. You see the diffuse dust at lower temperature. You can see that most of the emission is from the left side, which we don't have outflows. The outflow is on the right side. Particularly if in the velocity map of the outflows, we overplot the contours, we clearly see the presence of a cavity on the direction of the outflows, like that outflow is clean up channels in the galaxy. So in conclusions, yes, so current observation seems to suggest that there is a feedback in this galaxy, but we need high angle resolution, both in the near infrared, but also in the millimeter observations. And the detection of dust emission in quasar is not a proof of that negative feedback doesn't work. So thank you.
Excellent. Thank you, Stefano, for that great talk. Any questions? I'm giving like a minute for anybody to post any questions in the Q&A. And in the meantime, I wanted to ask, well, like this future high angular resolution observations that you're like aiming to get, like how are you planning to do so?
So far, most of the observation have been obtained in single limit or with ALMA with angular resolution about 0.6 arc-second. The idea is to go at least to below 0.2. It's better to have resolution, to have observation with solution about 0.1 arc-second to see the central part of the galaxy.
Yeah, and be able to remove that central dust component as we did before. Excellent. Thank you so much. Well, I don't see any questions there, but remember that the discussion goes 24/7 on Slack. so you can ask Stefano questions at any point. Thank you so much. I wanted to first thank all of the speakers for the talks today. Such interesting new science that is going to be very exciting in the new years to come. And all of the participants for the fantastic questions. I'm looking forward to continuing the discussion on Slack. And now somebody else is going to let us know.
Thank you very much, Paola. So we have a break now. We'll do 15 minutes to just as we did before. So we'll be back at 12:25 Eastern time for starting the third and last session of the day. So thank you very much again, and thank you very much to all the speakers.